I didn't have time to. I was some urgent task. Okay, so topic of the lecture today is hierarchy theorems. So we will prove that so our main result is that P is not equal to X. So we defined this classes last time. So problems aside, well, further time is so there are problems in X. So obviously P is a subset of X, but we will show that it's a language in X that's not in P. And then similar for P space in X space, but that's for seminar. Or maybe I will have time to explain it. So last time there was one small theorem we didn't discuss, which is that the existence of universal Turing machine. And so I will not prove this because it's kind of boring low-level programming with Turing machines, but I will mention this. So the theorem says that there exists a universal Turing machine. Then for any other Turing machine, for every program, the Turing machine, if you give it a description of the machine and the program, it will output the same as other Turing machine. So the proof just builds a Turing machine that gets a description of a Turing machine, and a program simulates this the descripted machine. But we can even have something stronger. We can do this simulation efficiently. For every machine, we will only lose a constant factor on the runtime. So this is what not many people know, but it's relevant for the theorems that we prove later.
Can you repeat this? There is this it's just universal machine, yes?
Yeah.
That's
For every other Turing machine,
and
for every program.
Oh, it's
Yeah. So this is a string. So for every P in 0, 1 star. Okay, we can have it over any alphabet, more general, like sigma. It is input alphabet of Turing machine. So for every P, so the universal Turing machine will have the same output as M has, or the same result. Like if a string is accepted, then machine U will accept the pair. If M reject P, then machine U will reject. If M runs forever, is in an infinite loop, then U will also have an infinite loop.
And what is a crucial fact about
the runtime? Okay, let me write this. So okay. So let me write it. So and let me continue here. So the time. So I need an extra constant here. And time of U on this pair is bounded by C, where time and so this is complete theorem. Okay, let's just add one for the case that machine stops immediately. Otherwise, we're a bit in a problem. So the time that machine U needs is just a constant times more, that essentially a constant times more than the time machine M needs. But this constant here depends on machine M.
And module of M, it's just
So that's the length of the
size
description. Yeah, the size of the machine. Yeah, if you have a big machine, if it needs a big description, you need more time for simulation.
Thank you.
Yeah. Okay, I put square here. Probably it's a bit better, but it doesn't matter. I just some constant that depends on the machine. And so how does it work? So here, the description of the pair. So here we assume that description starts with machine M and then a description of the program. And so the machine U will carry the description of machine M with it. And on the way, modify the tape and simulate U. So you remember that we have that kind of computation history. So when we go from one step to next step, the changes are local.
Well,
And
the universal machine is just copy the description of tuning machine or turn back to read it and
yeah, so okay. And initially, so what the universal Turing machine receives is a description of M, and then some separation symbol, let's say some type of blank, and then a description of P. Or you can just, if you have good separate, something like this, a description of P. And so the machine will just start to simulate as a machine U will just move around the tape, but at its current position. So it simulates M. What is M doing? M is running over the tape and making local modifications. And U will follow these positions of local modifications. But while doing this, it will carry the description M with it. So when it moves at the end of the program P, it will just carry M with it and move everything, all information from P to the front.
And it is just a constant time to copy
to move M as a constant time. So but basically, when it moves right, it will take a part of P and move this to the front. And this, I think it's even homework exercise. So machine can just put in the memory a part of P and then move here while memorizing all the, just flipping. Yeah. But to flip a constant amount of information, it can use just a bigger number of states in the hand. Yeah. So that's kind of theorem that you're linear in the time. So people, I think in Zipser book they use, I'm not sure if they have this theorem, but some books have quadratic time here. They put a square here. Yeah, but we can't have a square here. Okay, if we have a logarithm, then it's okay. Even, yeah. Okay, but since you don't need to know the proof, it's just to make sense of the next proofs that I mentioned this. So I will just right away remove it to make space on the bar. Okay. So our task is written here. So let us well, we will first say also prove that halting problem is undecidable, but that's not on the colloquium. It's just a warm up to prove these things because it's basically the same proof. Okay. So in mathematics, there are two types of sets, countable and uncountable. Things that are countable, number of finite strings, integer numbers, rational numbers. So countable means you can put everything in a list, and every element of the set you will meet at some point in the list. For example, okay, it's a bit too boring, but you know, like how can you have all rational numbers in a list? So what is this list? Yeah.
Well, you just can use the matrix
Yeah, so we just keep the sum of numerator and denominator constant, like 2/1. Okay, then 1/2. That's 3/1, 2/2, 1/3, and so on.
Yeah.
And so we get the list, and every fraction you can think of. Oh, I forgot the negative one, so you need to alternate positive and negative. Okay, but you get the principle. So functions. So okay, the number of Turing machines, like up to renaming of sets of states, is it countable or uncountable?
Number of.
So imagine that we have canonical names for the set of states. We number them from 1 till some number, 1 till 100. So of course you can say there are uncountable many Turing machines because we can rename the set of states, but that's kind of cheating. So let us fix names for the set of states. And then what do we know about number of Turing machines? So what is a Turing machine? It's 5 tuple. Right? There is a set of states.
We have only finite the alphabet.
Okay, sorry, there is something in the chat. U nas jest zapisy. Recording, yes, it's streaming on YouTube. And okay, I can give you the link on YouTube in case maybe it's useful to have it. Where is our course? Okay, if something goes bad with internet connection, you can switch to YouTube and then get things with the delay. Okay, let's go back to Turing machines. So, so if we use canonical names, so we say that Q is of the form 1, 2 till S, for example, as is natural number. Yeah. And then we have alphabet. Let's also use canonical name 1, 2 till T, for example. Then what is the next thing is start state. It's just we can fix the number 1 here, so it doesn't matter which state we choose as start state. So we can just take an element here 1, and then there is a transition table, and then is accepting state. So number of things we can build, a number of 5, such 5 tuples. Is it countable or uncountable?
Well,
Yeah.
with some theories that help us.
Yeah. Okay, but then list them since you're expert and count it. No, okay. So sets of this form is just the same as natural numbers. We can put them in the list. Same for alphabets. Now, if we have 2 things that are countable, then we can put all the direct products into Cartesian product into a list, right? So all pairs of 2 things. So if A is countable and B is countable, then A times B is also countable. By the same trick as we used for fractions, right?
We can encode Q as just a number.
Yeah. So Q is a number, this is a number, this is just 1, and this is a subset of finite sets.
Which is also
So only finitely many choices. So of course we can put it in the list, and then also finitely many choices. So number of Turing machines is countable. Yeah. Number of decidable languages, countable or uncountable?
Well, yes, because it's not more than 2 machines.
Yeah, indeed. Yeah. So number of decidable languages countable. Okay. Now, number of languages, countable or uncountable? All languages.
And we have a finite alphabet or
Yeah, finite alphabet. No, all languages, not just computable languages.
no, it should be more than countable.
Yeah. Well, if alphabet has only one element, it's countable because then only the length. But if there are at least two elements, then it's uncountable.
It's just the number of words, 0, 1 words. It's already already uncountable. So
yeah. So we can associate. So let me go to another question, and you will see it's essentially the same. So number of infinite sequences, infinite bit sequences. This set, it's countable or uncountable? Uncountable. And the proof, it will be very important for this lecture. So how is the proof? So imagine we can make a list that contain all infinite sequences. So I will give you, like, just come up with random list 1, 1, 1, 0, 0, 1, and so on.
Isn't it the same like counters?
Counter proof and so on. I'm just filling in things. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, and then let us look at inverse diagonal and so on. So inverse diagonal will be 1, 0, 1, 0, 1, and so on. Okay, so now I will prove that whatever list I give you, this inverse diagonal cannot be in the list. And it's obvious, because if it was on the ith row, then we just look to the ith bit, and by construction, it's opposite. Right? So we see that this infinite sequences is not countable set. And so now languages we can associate with infinite set. Why? But just put off the sound and say something.
Do you hear me?
Yeah, I hear you.
Okay. I'm a bit lost here. Is it right that all of these sets are finite? So it means they're countable. States are finite. Alphabet, I think, is finite.
So everything here is finite, and that's the main reason why it's countable. Because okay, but the question is, how many 5 tuples do there exist?
Is it right that tuples of 2 finite sets are finite?
Yeah, but you're confusing. So Q and gamma is finite, but the number of Turing machines, so the number of 5 tuples is infinite. Because for every S, we have already a different machine. So number of Turing machines is clearly infinite. Yes? So every Turing machine is built from 5 tuple, and all these components are finite sets. You're right. But the question is not whether Turing machine itself is finite. The question is how many different Turing machines exist.
But all Turing machines are a product of...
but it's like natural numbers. So every natural number is finite, but there are infinitely many natural numbers. And so every Turing machine consists of finite objects, but there are infinitely many Turing machines. And then there's the question, can we put all the Turing machines in a list? Yes or no? And so I want to do this to prove to you that there exist non-computable languages. We will say that number of computable languages is countable, but number of languages is uncountable. So there must be languages that are not computable.
And also not decided.
Yeah, yeah, that's the same. Computable and decidable is synonym. It's the same. Yeah, I don't know any place where it's not synonym. So, okay, maybe there exists somewhere some book I don't know where it's not synonym, but okay, yeah. So it's clear now for you?
It's not, I think.
Okay, yeah.
I'm chatting with Nikita Lukyanenko.
Okay,
Maybe
cool.
will
Yeah.
help me.
Okay, so yes. And so now we looked at infinite sequences, the set of infinite sequences, and we proved that it's uncountable. Okay. Now I want to say that the set of languages is also uncountable. And so we can identify a language with infinite bit sequence. How we do it? We make a list of all finite bit sequences. So the empty string, then the 0, then 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, and so on. Okay, and now we can build an infinite bit sequences. We place using indicator function. So if empty string is in the language, we put 1. If 0 is, we put 0. 1, 1, 1, 0, 1, 0. And in this way, we built an infinite sequence. For every binary language, there is an infinite sequence, and vice versa. For every infinite sequence, there is a so there is bijection between them.
Well, it's just a binary encoding code for every language, yes?
Yeah, that's how we can. So since we know that this set is uncountable, we know that the number of binary languages is uncountable as well. And so now we finish the proof. There exist languages that are not undecidable. Actually, it's very easy to make a language that's undecidable.
Are you expected to remember to prove this on the colloquium?
I will not ask it. I will just ask P and these ones. But I give you, we will use diagonalization method. So I explain the proof when it's easy.
Could you then please repeat how did we prove that this one is uncountable with
that this set is uncountable? Yeah. Well, imagine that you tell me here is a list of sequences. You give me a list of sequences. And so I have to give you a sequence that's not in your list, and then I proved you fail. And so anyone for every list, we can do it.
Yeah.
And so we are done. Okay, so here is your list.
Yes.
And here is the sequence on which you fail.
This is the list.
Yeah, this is the list. And then I look at the diagonal elements, I invert them, and I say, here is a sequence that's not in your list. Yeah. So uncountable means yeah.
Thank you.
So just repeat, I mean, there are more people who have trouble. So uncountable means you cannot put the things in the list. So for every list, one can come up with an element and it does not appear in the list. If it's countable, like natural numbers, each time you give me natural number, 1,000, and then I can prove it's in the list 1, 2, 3, 4, 5, and so on. Just have to count for a long time. Then, okay. So, so here, but we can combine both steps. We can just say epsilon here, an empty string. The 0, the 1, the 0, 0, 0, 1. And so a 0 we think about being not in the language, or a 1 we think about being in the language. And so here So in particular, if I give you, if you give me Turing machines, then a list of Turing machines. So we said that the Turing machines are countable. So let's put them in a list. And 3 and 4 and 5. So 0 means that machine does not accept, so it rejects or infinite loop. And 1 means it accepts. Okay. So then here is the inverse diagonal. And so it is this language. So here I created a language that's not computable. So I gave you a specific one. Okay, and so what is halting problem saying?
That it isn't decidable.
Yeah, so deciding whether a machine halts on a certain input is an undecidable problem. Okay, and this follows from this construction. Imagine it was decidable, then hold this table was decidable. And then this language was decidable as well. Because if we give it a string, we just look to corresponding diagonal element, but it's a bit lower. We evaluate the table because we said it's decidable. And then we get this language. But since it doesn't appear, it's undecided. So here are all Turing machines. Okay, let me say it a bit more carefully. So what do we mean with halting problem is undecidable? But just halting problem is for extra problems. And so what is the halting set for Turing machines? And in Sipser book, there is the M in subscript because they consider more things. And so it is M and P for which M P halts. Well, this set is undecidable. And I guess you learned this in logic course. Didn't you have a logic course?
Not all of us.
Ah, okay.
But some
Yeah, like Vereshchagin used to teach, but maybe somebody else now. Okay, so what we have proven is that this set is undecidable. Again, the proof, if this was decidable, it means that we can compute all the stable and we can compute inverse diagonal. But since we have all the Turing machines here, we cannot compute. And so here we use a computable enumeration of Turing machines. We just go over all strings and check whether it's a description of Turing machine. Okay. And here we use existence of universal Turing machine, because to evaluate the stable, we need to be able to, given a description of Turing machine, to simulate it on a given program. Okay, so this is for warm up, or at least things to just explain all the ideas. Let us now go to our task of proving that P is not equal to X. So hopefully you recall how what is P? It's just the union of all machines. Sorry, I'd like the opposite. Union over C and n to the power C and X over C. And so there is a common mistake. Some people write 2 to the power Cn. And this is the old definition of exponential time. It is denoted like this. The letter E denotes this class. But it's a very unpleasant class because it's not closed under polynomial time reductions. But sometimes it is used in a pseudo-random generator, a real cool topic. I think you have a course in it in 3rd year or first half of 4th year. And so they will use this class, but we will not use it because of this closure problem. And this class is defined by n to the power c.
Without two or
No, with 2. 2 to the power n to the power c. And note that for powers, priority is first. Like the brackets are here, right? So 2 to the poly of n. Okay. And so clearly P is subset of X. I already said it, but now let's construct a language that's in X, but not in P. Okay. So what will we do? We will apply the same construction. So if we change nothing, then we come up with undecidable set. And it's not good because we want to find a language that's in X and not in P. So we are outside P is the good news. Bad news is that our language is also outside X. So let me rewrite this.
Yeah, well, it's just too much. We need to add some strict.
And not, so that's our new condition. So yes, it's too much. So what's the problem? There are machines here that work very long. And to evaluate this diagonal, it might be that some machine on some input runs for x time or something, like just a tower of exponentials. It's very easy to program this, but very bad idea to wait until it terminates. So what will we do if the machine runs too long? We will just artificially cut it off and interpret the result as 0 or 1. It doesn't matter how you interpret them.
And when we call that it is running too long, we just have a constant on the input, or
yeah, so we say that if it runs for time 2 to the power input length, so here if this is x, then we run it for time 2 to the power length of x.
and if it's not halting, then we just
Yeah.
stop and
Yeah, we just stop and then we output something, not important what.
okay.
Yeah. Okay. So now what do we think? So now we just redefine the table. Okay. So before we said if machine does not accept, we write 0, and if it accepts, we write 1. And now let us say that if machine accepts in time less than this time, in this many steps, then we write 1. Okay. This is kind of a bit fuzzy because now we want to prove that this language in X. No, it works. Yeah, no problem. No, doesn't work. Because we can have a bit of a problem. We can have a huge Turing machine, and just simulating one step might take a lot of time. But with this simulation theorem, it's not a problem. So simulating 2. Okay, so yes. So the simple construction actually worked because I wrote a better universality theorem. So we simulate for this number of steps.
Mhm.
Okay. And now we need to make sure that the simulation runs in exponential time. How can we prove it?
Well, because 2 to the power of length of the inputs is exponential comparing to the length of the input. So if x the length of the input.
Yeah, so here we want to know whether X is in the language or not. So this is our language. And now we are so we have to prove 2 things. That this language D bar is in X and D bar is not in P. It's our task. Okay, so let us start. Yeah.
If our machine is halting on the time 2 to the power of length of x, then it's surely in x. Isn't it?
Yeah, so it's not so clear, it's not so obvious, because the simulation, so the simulated machine, so there are two definitions. So if simulated machine, if we run simulation for this number of steps, we need to prove that we compute the simulation in exponential time. So we need to think about the time needed to simulate one step.
X multiplied by
Yeah. But x,
the size of x.
yeah, it's indeed size of x, length, so the length of x, and I took the square times the constant, was the time needed for one step. Well, roughly there, I put it some +1 to it, okay. So that's the time for one step.
Two in the power of.
Yeah, so that's the number of steps we need, and so the runtime, it is still 2 to the power order length of x.
Why is that one step? It's just length to the.
It's
power?
from this theorem I wrote on the board in the beginning of lecture. I said that the time to simulate a machine was length of description.
Okay.
Yeah, squared times constant.
I need that to.
And so now we look, we want to know whether the x element belongs to the language not D. So that means we have to look to the machine whose description is x. And so here is the description of the machine. So the length of x is what was in this theorem, the length of the description of M. So, and the theorem said, remember, time of M times the length of the machine squared times constant. And so here we have this thing squared times constant.
So we just pick one of the machines, take its description, and run every machine to the time.
But to check that D is an X, so that's our question. Is it an X?
Yes.
Then we get as input a string. Here is a string, for example, 0, 0.
Okay.
Then we have to check which machine we're using to simulate. And this machine has description X, because we're going to this element of the diagonal. And then we simulate it with argument X. So we take machine, we take description, interpret it as machine, and give it as argument itself, and then negate the answer.
So machine just
run machine on its own description and negate the answer. But we cut off after this many simulated steps. Okay. So then we're done. But okay. So for this, we have to do we don't have simply a universal Turing machine.
So what we did now is just reconstruct the language, which is decidable on the time of
in X. We now want to prove that this inverse diagonal is an X. Okay, but there is a small problem, because we also said that the machine has to count its steps, and in the construction and theorem of universal Turing machine, we didn't have this this counter of steps. So how will we solve it? Well, we can solve it by using two tape machine, and on the second tape we count the steps. We go up, and then so at any moment the number is bounded by 2 to the length of x. So on the second tape, the length of the number is bounded by x, length of x. And so one step adds just an additional factor, length of x. But that is on two-tape Turing machine. We need one-tape Turing machine because all our definitions will go on one-tape Turing machine.
So it's to the power 2.
No, square.
No,
So we have
to the
to-
power 2.
Yeah. Sorry. Yeah. So we take the square, but it's still x, but this is still true. And so when we take square, then just the coefficient doubles, but it's still exponential time. Okay, so now we did first job. We proved that this inverse diagonal element is an X. So now, second job, we have to prove that this inverse diagonal is not in P. Okay, so some people don't look happy. So say something.
Well,
yeah, okay. I need to, but just, okay. So now second task, we have to prove that this inverse diagonal is not, well, let me adapt the notation, is not in P. Okay. So now, let us assume that there is a machine that runs in polynomial time. So then this machine, just think about the machine runs in polynomial time because we need it for definition of P. And let us say this is machine number 4 runs in polynomial time. Let's say it runs in time n to the power 6, or on input x, it runs in time x to the power 6 times 10 to the power 500. So that's bound on running time of the machine. It's polynomial time machine. And we need to prove that this does not belong to the list. So it's a bit of a problem. Because we know that on the fourth input, the answer will be different. But here we have polynomial bound, but we cannot write 2 to the length x when x is this 2-bit string. Because this is 4 and this is much larger when length of x equals 4. So we are not yet done, but we are done. Because when we make a list of descriptions of Turing machine, every machine appears infinitely often. So when you have a machine, you can always add junk states, states that are not reachable, like queues. Just make it artificially long, the description of the machine. And so its input the corresponding input will be artificially long, and we will be arbitrarily far on the diagonal. And so we just pick a machine 4 million, for example, or 4 billion. Let's imagine that this machine computes the same language as this machine in the same time. It's the same machine just with junk states. And then for this machine, we will have, so this equality will be valid. And that means that the machine is not blocked when we compute the table. So the machine is simulated until it's finished, right? Because if the length of x is 10 to the power, I didn't take enough. So I must say 10 to the power and 10 to, okay, just take a ridiculously large number. And then this equality will be valid. If length of x is equal to 10 to the power 10, we are good, right? So imagine that this machine simulates this machine. Then we will see that at this position, 10 to the power 10 to the power 10 is very far. We will have a conflicting answer with the diagonal. And so it means that D differs from this machine, and this machine is the same as the language computed by this machine. And so our original claim, for every polynomial time machine, there is an index, very far one, that disagrees with this index. So we just selected 2 machines that have the same sequence, and then realized very far there is a conflict. And so we conclude that N4 does not compute D. And I said we can do this for every machine that runs in polynomial time. We can make this argument. Every machine that runs in polynomial time will give a different answer on some long string. And now we finished the proof of the time hierarchy theorem.
Can you now repeat the parts of why D isn't in D?
Okay, let's.
After that we explained why it's in X.
Yeah.
Why it's,
Why? Okay, so just think about any machine that runs in polynomial time. I will give you an input where this machine answers differently from D bar.
well, on the index of more than polynomial was well.
So how to find?
We can choose the index which is 2 to the power exponential size, and our machine can reach that index. And since we have infinite words, we always have that index. Huh? Am I missing something?
I cannot. It's too vague to understand. So
Okay.
yeah, but it's roughly correct answer. But maybe let's say for safety, let's repeat one more time.
Okay.
So, okay, here is a machine. It's here M4 in this example. We want to, and we believe it runs in polynomial time. So here is the polynomial. That's upper bound on runtime. We want to find an X where this machine answers differently than inverse diagonal. How we get it? Well, let us look to the fourth. So this is machine M4. Let's look to the diagonal. So maybe it's different, then we are good. But it can happen that machine simulates this and it hits this bound. This is the case if length of X equals 2, then it will hit this bound before it hits its running time and termination. But no problem. We just look to an equivalent machine, a machine that computes the same language, performs the same calculations, but it has much longer description because of junk states. Okay.
Why does it have junk states?
So we make a list of all Turing machines.
Okay.
And that means a Turing machine will appear like in its simple form, but it will also appear when we just make a naive list. It will also appear with a larger state space, and this state space do nothing.
Oh, so they decide the same language.
Yeah, they decide
okay.
exactly the same language.
Okay.
But now this description of the machine is much larger. So note that X is equal to description of machine, and here is the copy of the machine, until then. And this is a gigantic machine. Description length is, for example, 10 to 10 to the 10, to a huge machine. And for this machine, we can look to the diagonal element. So X will be much larger, and it will be this constant in the front, and it will be this power. So exponent will be much larger because it beats these two constants.
So if we choose the more giant machine we pick,
the bigger its input,
yes,
and
okay.
then we will be below the exponential bound.
Yes.
And so that means that this machine, that in the table we get the machine that the answer that this machine wants in the simulation. So we simulated for this many steps until it stops. So we simulate until it stops, except if it takes more than this many steps, but this won't happen now. So machine calculates the correct output, and in the diagonal it is inverted.
The last statement isn't clear.
Okay, so for the complex machine, M tilde.
Yes.
So recall, what is definition of table?
Yeah.
So given an X,
Yes.
yeah, oh, but you should ask this, yeah. Okay, given x,
X is, for example, 0, 0.
yeah, 0, 0. Look to machine with description 0, 0. And run this machine.
Why is this machine 0, 0? M4. Well,
Yeah.
the diagonal is
Yeah, so here are all the strings, a list of all the strings.
there are names of the machine.
Yeah, yeah,
And on the diagonal, we have the machine which is runs on this on its inputs on its description.
yeah, yeah. So here is x, and here we say whether inverse diagonal accepts or not. Accepts means 1, 0 means reject.
Reject is the
Yeah, it's not in the language D bar.
and why it is actually a problem? Well,
Okay,
I missed the
so we have two bounds, x and here. We need to be outside P, but in x. And in the beginning, we said that if we do not cut off the machine, we
Yes.
end up with undecidable language.
Yes.
The proof why halting problem is undecidable. Remember, it's undecidable language. So definitely not an exp. We must cut it off the simulation.
yes.
Otherwise, no chance to prove it's undecidable.
So
So we cut off simulation.
we cut off
After this many steps, we cut off simulation.
yes. We cut off all the languages which is decidable more than in X, which
No, no.
isn't decidable by exponential time or
No, if we have machine 4,
yes.
for example, we will simulate it. But we stop simulation after more than 2 to the length of x steps. And so here x is 0, 0
Okay.
in this example.
So M4 0, 1, 1, 1, 1 is for 2 zeros. It is decidable for 2 zeros.
So
It tells when we give it 2 zeros, yes?
yeah, when we give it 2 zeros,
Yeah,
then we use this machine. When we give it 5 zeros,
yeah.
then it will be a machine with bigger number, like 32 or something, machine 32.
We want to look on the diagonal, but in which bit we want to find the difference. So we want to find the language.
Yeah, so given a string x, we
Yes.
look at machine with description
Yeah.
x
Yes.
and invert the answer, provided this machine on this input runs in at most 2 to the length of x steps.
Okay, and then we look at the language with inverted answer or
Yeah. Yes.
I see. And about that language, what we should want to say?
That contains all x such that mx so this is our language.
And we want to say that that language isn't decidable in polynomial time.
Yeah.
Okay. So we picked a constant.
Yeah, so
And
let's say M4 runs. So we pick a machine
Yes.
and we assume it runs in, if a machine runs not in polynomial time, it will not decide D bar in polynomial time because only polynomial time machines can.
Okay,
Yeah.
we looked only on
M4,
polynomial time machines.
Yes, and let's take an example. It runs in time this time.
Why that time? It's just an
Just arbitrary example.
Okay,
Yeah.
okay.
But just I take strange constants to make you aware of problem.
Okay.
Okay.
With
Yeah.
when we give it
Yeah, the 0, 0, because 0, 0 is string number 0, 1, 2, 3, 4.
Okay, the description of M4 is 0, 1, 1, 1, 1,
Yeah.
0.
Or let me write M0, 0, for example.
Yes, but I'm talking about the fourth line in the table in the matrix.
No, M0, 0.
Yes.
Okay, yeah, I need to write it. I cannot combine it. So I need to say yeah, MX runs, no, M0, 0 on X runs time, this time. Okay.
Yeah.
Yeah. So if we place X by 0, 0, then, oh, sorry, there was a problem. Here should be X. And now if we substitute X by 0, 0, then we find here something that's much bigger than the runtime 2 to the X. So 2 to the power 2 is 4. And so this machine does not work to prove that if we are lucky and the machine runs in time, just X, length of X, then it's good. Then this will work. This input will work because the halting didn't kick in. It stops after 2 steps, but here the bound is 4. And so we are good. We have proven that in this case, in this.
So we just tell that there is a constant, exists a constant such that exists the language which are decidable with our machine and polynomial time.
Yeah. So so we will look at machines that run in polynomial time. So then we can fix a polynomial time bound for this machine.
It's just our constant, which 10 to the power 500, blah, blah, blah.
And so let us now think that M00 has a very good bound for us. So then let's fill in this diagonal element, the string 00 for our machine. And then we see, okay, it stops after 2 steps. So we run the simulation and then either it accepts, so we say 0, or it rejects, and then we flip the answer in D bar. And we know that this machine gives different answer on 00. So we know that language decided by M4 is different from D bar. But we can have bad luck. We can have bad luck if here is 10 to the power 500 times length of X. Now this machine still runs in polynomial time.
But its polynomial time is larger, is more than
2 to the power length of X when we set X equal to 0, 0. But then we are not finished with our proof yet.
Yes, because it's still in polynomial time.
Yeah, it's polynomial, but our simulation is too short. So the problem is that if this machine accepts,
yes,
then it will be the same answer. Sorry, if this all X and X reject in time 2 to the power.
Well, if it rejects 2, it's not a problem. If it is inverted stage.
Yeah,
Yes.
So if it accepts, then we get the same answer on 4, 4. And so we need to find a different element in our table where the answers for M4 differ. And then it's easy to do it because we just look to as a machine that decides the same language but has an artificially large description.
And it's easy to construct because we always can add the blank symbols or
exactly.
any trash. Yes.
Yeah.
That's good.
We add trash and then we have the same language. And then we compare this the diagonal element of this complicated machine to the diagonal. And here we see a difference. But since these two languages are the same, these are equal. So they are equal. We have found a difference between this and this. Okay. And so now you understand everything.
Let me ask a question again.
Yeah.
So we have the table, the first line is 0, 1, 0, 0, 0. The fourth line is 0, 1, 1, 1, 1, 0.
Yeah.
What does this give us? So what we
So it means that empty string is not in the language, 0 is in the language, 1 is in the language, 0, 0 is in the language.
okay.
Yeah, oh, that's an important point. So there are nice columns here. You're right. I found them by bit strings, you know.
So M00 gives us an square for 0, 0 in the time of polynomial time.
Yeah, so when we have a polynomial, then we know if we make x long enough, then this bound will not kick in. And so we find a machine with junk states, so that its description is longer than the bound we need for this inequality, 10 to the power 500 times x, smaller than 2 to the length x. So we find the length for which this is true, this inequality. So polynomial smaller than exponential will always be true for long enough argument. So when we have this length, we look to a machine whose description is longer than this threshold, than the special length, and then we look to the diagonal element for this threshold, for this machine.
Only at this point.
Yeah.
We look at the diagonal element. What does this give us?
Okay, so we have machine M tilde, whose
M tilde.
description length is bigger, so that this is okay. So when we set x equal to M tilde,
And they are deciding
then
the
this
same
is okay.
They are deciding the same language, but at the diagonal
Yeah, yeah.
element, it's inverse. Well,
Yeah.
just and it is our answer.
Yeah, exactly. So the language decided by M tilde is different from D bar. But by choice of M tilde, it's the same language as M4 or M00. And so we concluded that M00 gives a wrong answer on the input M tilde.
To consume too much time to compute the answer. Yes.
Yeah, so M tilde on input himself is fast enough for exponential bound because M tilde is very big.
Yes.
Yeah, and that's the proof. So M tilde is wrong. It means that M4 is also wrong
And why
because we choose them for same language.
why they should be different? Why they should have the different elements in diagonal?
It's by construction of inverse diagonal.
Yes. Okay. I see.
Yeah, but it only based on the condition. Yes.
And why do we care about that? So why, what's implications of that? That M00 gives wrong answer.
Then it means M00 is not deciding D bar. And that means this candidate is not a good machine to decide D bar in polynomial time. And we can do it for all polynomial time machines. So we say every polynomial time machine makes at least one mistake to decide D bar. And so if every polynomial time machine makes a mistake, we have proven this thing. So to prove this thing, we look at every polynomial time machine and we find a mistake.
But that mistake is not on the element that M00 is
Yeah, M00 is
doing
example, of
in
course. Yeah, I just want to say that M00 makes a mistake, but we can do it for M000, the same argument. So
No,
then it's
I
different
mean-
polynomial.
I mean, M00 is right in input 00 by construction. So this it computes one element of D of D.
So yeah, we've chosen M00 so that it's right because it's too slow because of this constant factor. So yes, that's right. But so if we are lucky, then M00 is wrong on input itself. Then the proof is finished for M00. But then I look to the other case and I chose a very big constant so that this condition fails when x is equal to 0, 0.
So to compute D score, we need infinitely many Turing machines.
Yeah, infinitely many Turing machines need to fail to decide D bar. So in this table, we use indeed infinite. I don't understand the question. So in this table, indeed, there are infinitely many Turing machines.
It was the question. I just checked that I'm.
Okay, yeah. Okay, so
D bar is all x's that are rejected because of too much time.
no.
No?
So D bar contains all
All
x's that are rejected fast. Yeah,
So
yeah, rejected fast. So if it's machine runs too long, we accept.
yes.
Yeah.
When do we use the bar again in this proof?
So we need to use it twice. We say that D bar is an X, but this was okay because it
Okay.
follows from simulation theorem. And then D bar is not in P. Okay, and so when we use it again, we use it again when we say that to decide D bar, it can simulate any Turing machine, provided we add some junk state. Any polynomial time Turing machine, perhaps after adding junk states. Yeah, there is the second time we use it.
This proof provided in the system.
Yeah.
So I completed it.
Read it again. Yeah, I'm a bit confused. You need to react faster when I mean it's every year. It's a long time. It's only proven in a full lecture. Now it's actually good because we have 10 minutes left. So I can say what is space hierarchy theorem and what is the more precise theorem. And then it's good timing. So, but just, I mean, it's very easy proof, but somehow it's difficult.
I'm not a student of theoretical.
Okay, yeah. Yeah, but it's not a lot. So there was somebody like 4 people left online. So I guess they fell asleep or they gave up. But yeah, but at least Kostya, is for you, it's okay. Or I can repeat more. There's 10 minutes left.
I didn't get one thing. So for example, we want to prove that D is in P, in P. Let's imagine that our proof works and all goes fine. That we can construct such machines to simulate D bar. It will be infinitely many but countable amount of machines to get.
You are proving that D is in X or D is not in P. Which part of the proof are you explaining? Talking about?
I don't really know. Let me think.
Okay, which part of the proof do you believe? You believe D bar is an X?
I don't really get each part.
Is definition clear of D bar?
Yes, we constructed by having all the machines and negating the result on
I make
each
a mistake
X.
here. I forgot. That's probably the. Oh, so
Yeah.
X should so please tell me if I do such idiotic thing. Tell me immediately. So machine X on input X rejects fast.
By construction, D is to compute D, we compute infinitely many Turing machines. So it already is in exponential space.
No,
Time.
so we need an algorithm that tells whether a given string is in D bar or not.
Mm-hmm.
So that means to decide in polynomial time. It's definition of P. Sorry, yeah.
And for that we just use one machine, so it.
Yeah, and this one machine will be universal machine that counts number of simulated steps. And so why do we need universal machine? Because it has to run machine X on input X.
Okay. But again, we need infinitely many machines to do that because our
we
language
need one
is
machine, one universal machine.
Yeah.
That can simulate all of them. And so we have one machine. We need to construct one machine to prove this. And so then we use a theorem with efficient assimilation, and it goes very easy. But now we need to prove this, and now we need to say that infinitely many machines make a mistake in some input. So we need to say that each machine that runs in polynomial time makes at least one mistake on some input.
So. And that proves that we need all of that machines.
Yeah, so we need to look at all machines that run in polynomial time. Yeah, and so we need to find the input for the machine where it's wrong. And when we are lucky, it's just the description itself. This input already gives different answer. But if we can be unlucky because of this restriction on time bound, we need to reject fast. maybe it rejects, but it's rejecting slowly. And then we have a problem, and that's why we think about this machine with extra junk states. Thanks to the extra junk states, the runtime on itself does satisfy this bound, this exponential bound. Okay.
What is the E at the bottom of the so
D bar.
D bar is
So it's
the
the same
sequence
thing.
of one.
Oh, yeah, 1 0 1 0. So it means that if this string is accepted, there is 1. If this string is in outside D bar, it's 0. So for example, string 0 0, we look at the column for 0 0.
Yes.
If there is a 0, that means 0 0 is outside. Otherwise, it's in. So here we go over empty string. Then the string 0, the string 1, the string 0 0 is here. String 0 1, and so on. Yeah.
Is it what we call the upper?
Yeah, that's the same language here.
We will talk about this space and next space today, or
I will just, that's for the seminar. It's the seminar exercise.
So we're finished.
Well, there exists a precise time and space hierarchy theorem, and you need it for the exercise. So I will write it, the statements, and then we are finished. So it's like 5 minutes late, we will be. So it requires, okay, I
Are
will,
we going to prove the hierarchy theorems or?
so the fine hierarchy theorems, I mean, the proof is all the same. Just here we have a gap polynomial exponential. You will see that when we look.
And to the power 2.
Yeah, okay, I will just explain it, and then we are finished. Because so now there is also when we look to finer hierarchy, for example, time to the power 4 is a strict subset of time to the power 6 and to the power 5. So this can also be proven. Actually, we can go even finer. N to the power 5 log n is a strict subset. No, this is too fine. This works. So there is this fun thing. So as soon as we have strictly more than one logarithm factor extra in the time bound, we know that the classes are different. And so what's the most general, and I will now write down the most general statement.
So if we have n to the power 4 some logarithm to the power 1 plus epsilon.
Yeah, it also works. Yeah, just so let's write a full statement. If a function, so if a time bound is time constructible, then there exists a language in time f of n log n that is not in, I will soon explain what is time constructible. Is in not time g of n, and g should be little o of m. So this is time hierarchy theorem. No, I'm not going to prove it. It's also not for colloquium. Yeah, but this is proven in Sipser book. But the proof is no. Only P is not. Only these two results are in colloquium. Yeah. But the proof is the same, except I need to first define what is time constructible. And f is time constructible if you can compute f in time order f. So f is time constructible if there exists a Turing machine, and that for all n computes f of n in time. Okay, for all n on input n computes f of n in time order f of. So that is time constructible.
We should
Here is definition. Here is theorem. Okay, and now you can understand the statement. The proof is essentially the same. So the only thing what we need is some small gap between the bound for simulation and so we need a cutoff time. And we need a little gap because the simulation takes a bit more time than it takes an extra factor of time. And one can push this extra factor down to a logarithm. So in the proof, I used the square, remember?
yes.
Yeah, but one can move it down to a logarithm. And it's just like in a one-tape Turing machine can carry the counter with it. And so at every move, it just needs to move the counter one step to the left or to the right. And the size of the counter is, sorry, it should be log f of n. And the size of the counter is log f of n. Okay. So that's how this result is proven. Okay, and then there is similar for space constructible. But in space constructible, we don't need this extra thing here. So here n is space constructible. And we can make it stronger. We just need a superlinear difference here. So G is small o of f. You learned about a small o, right?
Yes.
It's just that the ratio Gn of f of n.
So space constructible
is zero.
just can
That's
in space constructible.
Yeah. We only need the constant factor in the separation. I mean, we need better than constant, faster. And then there is one exercise where we even don't need the constant, but I kind of restrict the languages. Oh, sorry, the space constructible. Yeah, I've written it here. Everything is written. So for space constructible, the proof is a little bit different, more difficult, because there is a problem like for time bounds, we can just measure the, so we need to cut off the machine when it exceeds certain time. But for space, so if a machine gets in an infinite loop, then it will run out of time. And so we can still define the language. So a machine that gets in the loop. But for space, we will cut off if the machine uses too much space. But then the machine can still get in an infinite loop. So we also need to detect whether the machine is looping.
But we can,
Yeah.
because we have only f of n space, and we can just
Yeah,
count
count
the space
until some 2 to the power constant times f of n. If the machine runs longer than this, it means some state is used twice, and we discussed this in previous seminar. And that just doubles the space used by the machine.
But and it's
Yeah.
just a constant. It's not whether.
Yeah, exactly. And that's why we can do it. But the proof has extra part. And so maybe if Nikita will get there during the seminar, then you will learn about it. And otherwise, you will need to learn it by yourself in Sipser book.
We'll try to get with Nikita.
Yeah,
to that place, but
yeah, it's like 8 questions.
can we have some delay of start the seminar because
Yeah, it's 6 minutes late now, right?
Just-
I should stop at 7:30, it's 36 now. So then let's start the seminar 6 minutes late. So, yeah. I mean, the beginning of the seminar, Nikita is not allowed to say much because you have to think for yourself. Okay, I will try to print the seminar. Let's end.